Far beyond the reach of any human eye, James Webb pointed its mirrors at a patch of empty darkness and captured something that shouldn't exist. Light that has traveled for more than 13 billion years. Light carrying the signature of galaxies, so massive, so structured, so mature, that by every rule of our physics, they shouldn't have had the time to form. According to the models we swear by, these galaxies behave as if they're older than the universe that contains them. Not literally older, but older according to the laws we trust to measure space and time. And if that's true, then our timeline of the cosmos is broken. If you enjoy these deep dives, you can subscribe. It helps more than you think. So, let's begin. When the first images came back from Webb in the summer of 2022, the reaction among cosmologists wasn't celebration. It was closer to confusion. There were galaxies in those images that didn't fit. Too bright, too structured, too red in ways that suggested they were very far away, which also meant very early in time. And the more data came in, the more the discomfort grew. One galaxy in particular caught attention early on. It appeared as a faint smudge in the deep field, but its spectrum told a different story. The redshift was enormous. If that redshift was accurate, the light had been traveling for more than 13 billion years. The galaxy existed when the universe was less than 300 million years old. But it wasn't just distant, it was massive. It had the stellar mass of billions of suns, maybe more, and that's where the problem starts. In the standard model of cosmology, the one we call lambda CDM, the early universe is a place of simplicity. After the Big Bang, space is filled with hydrogen, helium, trace amounts of lithium, no stars yet, no galaxies, just gas, cooling and spreading, with tiny fluctuations in density that gravity begins to pull together. Dark matter, invisible but abundant, forms the scaffolding. It clumps first, creating gravitational wells where normal matter can fall and collect. Over time, millions of years, the gas grows dense enough to ignite the first stars. Those stars live, burn, die. Some explode as supernovae, scattering heavier elements. Slowly, over hundreds of millions of years, small clumps of stars gather into what we'd recognize as galaxies. It's a gradual process, a patient process. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old. At that point, it's still smooth. The seeds of structure are there, but they're tiny, 1 part in 100,000. To go from that smoothness to galaxies with billions of stars in just 200 or 300 million years more, you need everything to happen fast, faster than the models allow, and yet, there they are. Webb didn't just find one anomaly, it found many. Galaxies at redshifts above 10, above 12, even higher, each one pushing the timeline backward, each one more massive than seemed possible. Some appeared to have already assembled into compact, dense structures. Others showed signs of having undergone multiple generations of star formation. You could see it in their spectra. The light carried the fingerprints of elements that only exist because stars have already lived and died. Carbon, oxygen, nitrogen, elements that require time. The deeper Webb looked, the more crowded the early universe became. What was supposed to be an era of darkness, a time between the fading of the cosmic microwave background and the lighting of the first stars, seemed instead to be filled with light. Galaxies everywhere, bright, massive, structured. Too many of them, too soon. Before we go further, it helps to understand what we're actually measuring when we look at these distant objects. The universe expands. That expansion stretches everything embedded in space, including light. When a photon leaves a distant galaxy and travels toward us through expanding space, its wavelength gets longer. Blue light shifts toward red. Ultraviolet shifts into the visible spectrum. Visible light shifts into infrared. The farther the light travels, the more space expands during its journey, and the more the wavelength stretches. This stretching is what we call redshift. It's quantified with a number, usually denoted by the letter Z. A galaxy with a redshift of Z equals 1 has had its light stretched by a factor of 2. A galaxy with Z equals 9 has had its light stretched by a factor of 10. The relationship isn't linear, but the principle holds. higher redshift means more stretching, which means more distance, which means more time. But here's the thing, redshift alone doesn't tell you distance. It tells you how much space has expanded since the light was emitted. To convert that into an actual distance, you need a model of how the universe has expanded over time. You need to know the rate of expansion at different epochs. You need to know the density of matter, the density of dark energy, the curvature of space. All of that is encoded in lambda CDM. The standard model gives us the equations that connect redshift to distance and distance to time. When Webb observes a galaxy and measures its redshift, it's using the light from that galaxy to work backward through cosmic history. The spectrum shows absorption and emission lines from elements in the galaxy's stars and gas. Those lines have characteristic wavelengths when measured in a laboratory. In the galaxy's spectrum, they appear shifted toward redder wavelength. By measuring how much they've shifted, you get the redshift. Then, you plug that redshift into the cosmological model, and it tells you how far away the galaxy is and how long ago the light was emitted. This process has been refined over decades. It's not guesswork, it's based on solid physics and extensive observations, but it depends entirely on the model being correct. If the model is wrong, if the expansion history of the universe isn't what we think it is, then the distances and times we calculate are wrong too. And that's part of what makes the Webb findings so unsettling. The redshifts themselves are reliable. They're measured from spectral lines. But the interpretation of those redshifts, the translation into cosmic time, depends on lambda CDM. And lambda CDM says that a galaxy at redshift 12 existed when the universe was about 400 million years old. It says that the light we're seeing left that galaxy 13.4 billion years ago. And it says that in those first 400 million years, there wasn't enough time for galaxies like the ones we're seeing to form. So either the measurements are wrong, or the interpretation is wrong, or the model is wrong. Those are the options. At first, many astronomers leaned toward the idea that the measurements were wrong. Early mass estimates for galaxies are tricky. You observe how bright a galaxy is, and you use that brightness to estimate how many stars it contains. But brightness can be deceptive. A galaxy might look bright because it has a lot of stars, or because it's forming stars very rapidly at the moment we're observing it, or because we're seeing it during a brief phase when it's particularly luminous. Young, massive stars burn hot and bright, but don't last long. A galaxy going through a burst of star formation can appear much more massive than it actually is if you're not careful about how you interpret the light. Dust also complicates things. Dust absorbs and scatters light, especially at shorter wavelengths. A galaxy obscured by dust might appear redder than it actually is, which could lead to an overestimate of its redshift, or it might appear dimmer, which could lead to an underestimate of its distance. Disentangling these effects requires detailed modeling and often multiple observations at different wavelengths. So the first wave of skepticism was reasonable. Maybe these galaxies weren't as massive as they seemed. Maybe their redshifts were lower. Maybe there were instrumental effects or observational biases that hadn't been accounted for. But as more data accumulated, that explanation became harder to sustain. Follow-up observations with spectroscopy confirmed many of the high redshift. The galaxies were really that far away. And while some mass estimates were revised downward, the overall trend remained. There were too many massive galaxies too early. Even accounting for uncertainties, even being conservative with the estimate, the population of early galaxies was larger and more mature than lambda CDM predicted. One of the galaxies that became emblematic of this problem was catalogued as JWST Z13 The name is technical, derived from the survey program and the galaxy's position in the sky, but the object itself is remarkable. Spectroscopic observations confirmed its redshift at just over 13. That places it at a time when the universe was only 320 million years old. The galaxy is compact, only a few thousand light years across, but it's forming stars at a rate that suggests it already contains a substantial stellar population. To have accumulated that much mass in such a short time requires star formation to have started almost immediately after the cosmic microwave background faded. And it's not alone. Multiple galaxies with similar or even higher redshifts have been identified. Some appear to be forming stars at rates of tens or even hundreds of solar masses per year. That's fast, very fast. In the local universe, a galaxy like the Milky Way forms maybe 1 or 2 new stars per year on average. These early galaxies seem to be operating at a completely different pace. The question then becomes, how? How do you get that much star formation that early? Stars form when clouds of gas collapse under their own gravity. But gas resists collapse. It has pressure, it has temperature, it has turbulence. For a cloud to collapse, it needs to cool down so that the pressure decreases and gravity can take over. In the present-day universe, that cooling happens through the emission of radiation. Atoms and molecules in the gas collide, get excited, and emit photons. Those photons carry energy away, and the gas cools. But in the very early universe, there aren't many heavy elements yet. The gas is almost entirely hydrogen and helium, with trace amounts of lithium. Hydrogen can cool through certain atomic transitions, but the process is slow. Helium is even worse at cooling. Without efficient cooling, clouds stay warm and diffuse. They don't collapse easily. They don't form stars quickly. The first stars, the ones that formed in this pristine gas, are thought to have been very different from stars today. They're called population the 3 stars, and they're purely theoretical. We've never observed one, but the models suggest they would have been massive, hundreds of times the mass of the Sun. They would have burned through their fuel in just a few million years and then exploded as supernovae, enriching the surrounding gas with heavier elements. Those heavy elements would have made it easier for the next generation of stars to form because carbon, oxygen, and other elements are much better at radiating away energy. They cool the gas more efficiently. So, the conventional picture is that the first stars were big and short-lived, and they seeded the universe with the elements needed for more normal star formation. Over time, as more stars formed and died, the gas became more enriched, and galaxies gradually assembled. But this process takes time. You need the first stars to form, live, and die. You need their supernova ejecta to spread out and mix with the surrounding gas. You need that enriched gas to cool and collapse into new stars. Each step has a timescale associated with it. The galaxies Webb is seeing seem to have skipped ahead. They show evidence of multiple generations of stars. They have heavy elements in their spectra, but they exist at a time when, according to the models, only 1 or 2 generations should have passed, maybe 3 at most. One way to resolve this is to make star formation more efficient in the early universe. If the first stars formed faster, if they lived and died more quickly, if their supernovae dispersed material more rapidly, you could compress the timeline, but there are limits to how much you can compress it. Stars have a minimum lifetime determined by how fast they can burn their fuel. Supernova ejecta expand at a finite speed. Gas cooling happens at a rate governed by the physics of atomic and molecular transitions. You can adjust the parameters, but you can't break the underlying physics. Another possibility is that the first galaxies formed from gas that was already partially enriched. Maybe there was some process, something we haven't accounted for, that scattered heavy elements through space before the first stars even formed. That sounds unlikely, but it's not impossible. There are speculative ideas involving primordial black holes or exotic physics in the very early universe that could, in principle, produce enrichment without stars. Primordial black holes are a fascinating possibility in their own right. Unlike the black holes that form from collapsing stars, primordial black holes would have formed directly from density fluctuations in the early universe. If the density in a particular region was high enough, it could have collapsed into a black hole almost immediately after the Big Bang. These black holes could have been any mass, from microscopic to thousands or even millions of solar masses. If there were massive primordial black holes in the early universe, they could have acted as seeds for galaxy formation. Matter would fall toward them, forming an accretion disk. The disk would heat up, radiate energy, and some of that energy would drive winds that compress surrounding gas clouds, triggering star formation. A galaxy forming around a massive black hole could, in principle, assemble faster than one forming from scratch. There's also the possibility that primordial black holes could merge with each other, growing larger and creating even stronger gravitational wells. The more massive the black hole, the more matter it can attract, and the faster the surrounding galaxy can grow. This could explain why some of the early galaxies Webb has found seem to have assembled so quickly. But there's a problem with this idea. We don't have direct evidence for primordial black holes. They're predicted by some models of the early universe, but we've never detected one. And if they were common enough to explain the rapid formation of early galaxies, we'd expect to see other signatures of their presence, gravitational wave signals from mergers, for example, or lensing effects in the cosmic microwave background. So far, we haven't seen those signatures. That doesn't mean primordial black holes don't exist, but it does mean we can't rely on them to solve the problem without more evidence. Then there's dark matter. We know dark matter exists because we can see its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. It makes up about 85% of the matter in the universe, but we don't know what it is. We don't know if it's a single type of particle or a mix of different particles. We don't know how it interacts with itself, if at all, beyond gravity. In the standard model, dark matter is assumed to be cold, meaning the particles move slowly compared to the speed of light. Cold, dark matter clumps efficiently under gravity, forming the scaffolding that guides where galaxies form. But there are variations on this idea. Maybe dark matter isn't entirely cold. Maybe some fraction of it is warm or hot, moving faster and clumping less efficiently. Or maybe dark matter particles interact with each other in ways we haven't detected, allowing structures to form differently than we expect. Some researchers have proposed that if dark matter has self-interactions, if the particles can scatter off each other, that could change how quickly structures form in the early universe. Self-interacting dark matter might collapse more rapidly in dense regions, creating stronger gravitational wells that pull in normal matter more efficiently. This could speed up galaxy formation, but again, this is speculative. We don't have evidence for self-interacting dark matter yet. It's an idea that's being explored, tested, against observations, but not confirmed. Another angle involves the expansion history of the universe itself. Lambda CDM assumes a particular form for how the universe has expanded over time. Right after the Big Bang, expansion was rapid. As the universe aged, the expansion slowed due to the gravitational pull of matter. Then, a few billion years ago, dark energy started to dominate, and the expansion began accelerating again. This history is encoded in the equations that relate redshift to time and distance. But what if that history isn't quite right? What if the expansion rate in the early universe was different from what we think? If the universe expanded more slowly in the first few 100 million years, that would give more time for structures to form. The redshifts we measure would correspond to later times than we currently calculate. A galaxy at redshift 12 might actually have existed when the universe was 600 million years old instead of 400 million years old. That extra time could be enough to allow the galaxy to form. This idea runs into problems with other observations, though. The cosmic microwave background is exquisitely sensitive to the expansion history. The patterns we see in the CMB depend on how fast the universe was expanding at the time the CMB was emitted. Any significant change to the early expansion rate would alter those patterns in ways we should be able to detect. And so far, the CMB matches the predictions of Lambda CDM very well, so you can't just change the expansion history without breaking something else. There's also the issue of the Hubble constant, the rate at which the universe is expanding today. Measurements of the Hubble constant from different methods have been giving slightly different values, a discrepancy known as the Hubble tension. Some measurements, based on observations of distant supernova and the cosmic distance ladder, suggest a higher value. Others, based on the cosmic microwave background, suggest a lower value. The difference is small, only a few percent, but it's persistent and statistically significant. Some researchers have wondered if the Hubble tension and the early galaxy problem are related. Maybe there's something about the expansion history we're missing, something that affects both the present-day expansion rate and the formation of early galaxies. but connecting these two issues in a consistent way has proven difficult. Most proposed solutions to the Hubble tension don't naturally explain the early galaxies, and vice versa. Modified gravity is another avenue people have explored. General relativity, Einstein's theory of gravity, has been tested extensively and holds up remarkably well. But all of those tests have been done in relatively low energy, low curvature regimes. The solar system, binary pulsars, gravitational waves from merging black holes. We haven't tested general relativity in the extreme conditions of the very early universe or at the largest cosmological scales. Some alternative theories of gravity predict that gravitational attraction could be stronger under certain conditions, which would make structures form faster. Or they predict modifications to how gravity behaves on cosmological scales, which could change the expansion history or the growth of density fluctuations. These theories are mathematically complex and often come with their own set of problems. They might solve one issue, but create new tensions with other observations, and most physicists are reluctant to modify general relativity unless absolutely necessary, because it works so well in so many contexts. Still, the early galaxy observations have prompted some theorists to revisit these ideas. If lambda CDM can't accommodate the data without significant adjustments, maybe it's worth looking at alternatives, not as a first resort, but as a possibility to keep in mind. There's another layer to this problem that doesn't get talked about as much: the way we estimate galaxy masses. When we observe a distant galaxy, we see the light it emits. That light comes from stars, mostly, but also from gas clouds, and sometimes from active galactic nuclei powered by supermassive black holes. To figure out how many stars the galaxy contains, we have to model what kind of stars are producing the light we see. Different types of stars contribute differently to a galaxy's brightness. Young, massive stars are extremely luminous but short-lived. They dominate the light output of a galaxy going through a burst of star formation. Older, less massive stars are dimmer but longer-lived. They dominate the light from a quiescent galaxy that stopped forming stars a long time ago. The same galaxy can look very different depending on its star formation history. To estimate the stellar mass, astronomers fit models to the galaxy's spectrum or its brightness at different wavelengths. They try different combinations of star types, ages, and star formation histories to see which one best matches the observations. But this process involves assumptions. You have to assume something about the initial mass function, the distribution of masses for newly formed stars. You have to assume something about dust extinction, how much light is being absorbed and re-radiated at longer wavelengths. You have to assume something about the metallicity, the abundance of elements heavier than hydrogen and helium. All of these assumptions can affect the mass estimate. If you assume the wrong initial mass function, you might overestimate or underestimate the number of stars. If you don't account for dust properly, you might get the wrong luminosity and therefore the wrong mass. If the stars in these early galaxies have different properties than stars in the present-day universe, your models might not apply. Some researchers have argued that the early mass estimates from Webb were too high precisely because of these modeling uncertainties. Maybe the galaxies are less massive than initially thought. Maybe they're just unusually bright for their mass, because they're forming stars at a prodigious rate. As more detailed observations have come in, some of those mass estimates have indeed been revised downward. But even with the revisions, many of the galaxies remain more massive than lambda CDM comfortably allows. And it's not just about individual galaxies. It's about the population as a whole. Even if each galaxy is somewhat less massive than first estimated, there are a lot of them. The number density of massive galaxies at high redshift, the number per unit volume of space, is higher than predicted. Lambda CDM says that massive galaxies should be rare at early times because there hasn't been enough time for them to assemble. But Webb is finding them all over the place. This is where statistics come in. 1 or 2 anomalous galaxies could be outliers, statistical flukes, or objects that formed under unusual circumstances. But when you find dozens of them, the explanation has to account for all of them. Either they're all outliers, which is unlikely, or there's something systematic going on. Either the observations are systematically biased in a way we haven't recognized, or the models are missing something important. The scientific community is still working through these possibilities. New papers come out regularly, proposing different explanations, testing different hypotheses, analyzing the data in different ways. Some argue that the problem is overstated, that the galaxies can be explained within the standard model with reasonable adjustments to star formation, efficiency, or dust corrections. Others argue that the problem is real and significant, that lambda CDM is being stretched to its breaking point. There's a certain tension in how scientists talk about this. On one hand, there's excitement. These are genuinely puzzling observations. They're pushing the boundaries of what we know. They're forcing people to think carefully about assumptions they might have taken for granted. On the other hand, there's caution. Nobody wants to declare a crisis prematurely. Nobody wants to abandon a successful model based on incomplete data. And nobody wants to hype up a problem that might resolve itself with more observations. The history of cosmology is full of moments where observations seemed to contradict theory, and it turned out the observations were wrong or misinterpreted. But it's also full of moments where the observations were right and the theory had to change. Distinguishing between those two situations requires time, more data, and careful analysis. What makes this case particularly interesting is that it's happening in real time. Webb has only been operating for a couple of years. The data is still coming in. The analysis is still being refined. We're watching the scientific process unfold with all its uncertainty and debate, and that process doesn't move as fast as people sometimes expect. Science isn't about jumping to conclusions. It's about testing ideas rigorously, considering alternatives, and building a consensus based on evidence. One of the things that gets lost in discussions about these early galaxies is just how difficult it is to observe them. They're incredibly faint. Even with Webb sensitivity, detecting them requires long exposures, sometimes tens of hours, staring at a single patch of sky. And even then, the galaxies appear as tiny smudges, often just a handful of pixels in the image. Extracting meaningful information from those smudges requires sophisticated analysis. Spectroscopy, the technique of spreading light into its component wavelengths, is particularly challenging for these objects. Because they're so faint, getting a spectrum with enough signal to measure redshifts and identify spectral features can take many hours of observation time, and telescope time is precious. Webb is oversubscribed by a factor of several times, meaning there are far more proposed observations than the telescope can actually perform. Every hour spent observing one galaxy is an hour not spent on something else. So the data we have, as impressive as it is, represents only a small fraction of what's out there. We're sampling the early universe, not surveying it completely, and sampling introduces biases. We're more likely to detect the brightest, most massive galaxies because they're easier to see. There could be a population of smaller, dimmer galaxies that we're missing entirely, and those missing galaxies might change the overall picture. This is something astronomers are acutely aware of. When you talk to people working on these observations, they're careful to note the selection effects, the incompleteness of the samples, the uncertainties in the measurements. The popular narrative often focuses on the surprising or dramatic findings, but the reality is more nuanced. The data is complex, the analysis is challenging, and the conclusions are provisional. That said, the trend is clear enough that it's taken seriously. The number of massive, mature galaxies at high redshift is higher than expected. That much seems robust. Whether it's high enough to require major changes to lambda CDM is still being debated. But it's not a debate happening at the fringes. It's a mainstream conversation involving leading researchers at top institutions. Part of what makes this so compelling is the sheer ambition of what we're trying to do. We're looking at light that's been traveling for over 13 billion years. We're trying to reconstruct the history of galaxies from that light, to understand how they formed, how they evolved, how they grew into the structures we see today. And we're doing it with instruments that, as powerful as they are, can only give us partial information. Every photon that reaches Webb from one of these distant galaxies is precious. It carries information encoded in its wavelength, its arrival time, its polarization. By collecting enough photons and analyzing them carefully, we can learn about the stars that emitted them, the gas that surrounded those stars, the gravitational field that shaped the galaxy, the expansion of space that stretched the light on its journey. It's an astonishing amount of information to extract from something as ephemeral as light, but it's also indirect. We never see the galaxies as they are now. We only see them as they were. And the farther back we look, the more we're relying on models to interpret what we see. Models of stellar evolution, models of galaxy formation, models of cosmic expansion, models of radiative transfer through gas and dust. Each model has uncertainties, and those uncertainties compound when you try to connect observations to physical properties. So, when we say a galaxy appears to be older than the universe, what we really mean is that the physical properties we infer from the observations seem inconsistent with the time available according to our models. It's a statement about the mismatch between observation and theory, not about the galaxy itself. The galaxy is just doing what galaxies do. It formed, it gathered mass, it made stars. It doesn't know or care about our models. This is the humility that cosmology demands. We're building a picture of the universe from fragmentary evidence. We're extrapolating from what we can see to what we can't. We're testing theories that describe events billions of years in the past, far beyond anything we can directly verify. And sometimes, the picture we've built doesn't quite fit the new evidence. That's not a failure. It's an opportunity. The standard model of cosmology is one of humanity's great intellectual achievements. It takes us from the first fractions of a second after the Big Bang to the present day, across nearly 14 billion years of cosmic history. It explains the cosmic microwave background, the large-scale structure of the universe, the abundance of light elements, the expansion rate, the formation of galaxies and stars. It's been tested against countless observations and holds up remarkably well, but it's not complete. It doesn't tell us what dark matter is. It doesn't tell us what dark energy is. It doesn't describe the physics of the Big Bang itself, only what happened afterward. It doesn't explain why the universe has the particular properties it does, why the expansion rate is what it is, why the density fluctuations that seeded galaxies have the amplitude they do. These are questions that go beyond the standard model. And now, Webb is adding to that list of open questions. Why are there so many massive galaxies so early? How did they form so quickly? What does their existence tell us about the physics of the early universe? Are we missing something in our understanding of star formation, or galaxy formation, or cosmic expansion? Or are we missing something deeper, something about the nature of gravity, or dark matter, or the initial conditions of the universe itself? These aren't questions with easy answers. They require more observations, more analysis, more theoretical work. They require patience and rigor, and a willingness to follow the evidence wherever it leads, even if it takes us to uncomfortable places. One of the things that's often misunderstood about science is that uncertainty isn't a weakness, it's a feature. Science doesn't claim to have all the answers. It claims to have a method for finding answers, a way of testing ideas against reality. When observations don't match predictions, that's not a failure of the scientific method. That's the method working as intended. You make a prediction, you test it, and if the test fails, you revise your understanding. The early galaxy observations from Webb are a test of lambda CDM, and by many measures, the model is passing. It predicted that there would be galaxies at high redshift, and there are. It predicted that those galaxies would show certain properties, and many of them do, but some of them don't. Some of them are more massive, more structured, more mature than expected, and that discrepancy is what's driving the current discussion. It's worth noting that lambda CDM has been through this before. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe was accelerating. That wasn't predicted by the models at the time. In fact, it was the opposite of what was expected. Most cosmologists thought the expansion should be slowing down due to gravity. The discovery of cosmic acceleration was a shock, but the standard model adapted. dark energy was introduced to account for the acceleration. The cosmological constant, a term in Einstein's equations that he'd once considered his greatest blunder, was resurrected. Lambda CDM, the lambda standing for the cosmological constant, became the new standard model. It wasn't a complete overhaul, it was an addition, a new component that hadn't been recognized before. Something similar could happen with the early galaxy problem. Maybe there's a component or a process we haven't included yet. Maybe the models need an adjustment rather than a replacement. Or maybe the observations will turn out to be less anomalous than they currently appear. More data could shift the picture. Better mass estimates, better redshift measurements, better understanding of selection effects. The field is still in the process of figuring it out, but there's also the possibility, however remote, that we're seeing the first signs of something more fundamental, that Lambda CDM isn't just incomplete, but wrong in some essential way, that the universe doesn't conform to our neat timeline, our assumptions about how structure forms, our equations for how gravity and expansion interact. That possibility is what makes this so compelling, not because anyone wants the model to be wrong, but because discovering where it breaks would teach us something profound. There's a parallel to draw with the history of cosmology in the early 20th century. Before Edwin Hubble's observations, most astronomers believed the universe was static and eternal. The idea that the universe could be expanding, that it could have a beginning, was seen as radical, almost philosophical rather than scientific. When Hubble measured the redshifts of distant galaxies and found that they were moving away from us, the evidence forced a paradigm shift. The universe wasn't static. It was dynamic, evolving, changing with time. That shift didn't happen overnight. There was resistance, debate, alternative explanations. Some astronomers proposed that light might lose energy as it traveled, causing a redshift without expansion. Others suggested that the observations were being misinterpreted, but the evidence kept accumulating, and eventually, the expanding universe became the accepted picture. It led to the Big Bang model, which in turn led to predictions about the cosmic microwave background, the abundance of light elements, the formation of structure, all of which have been confirmed. We might be at a similar juncture now, not necessarily as dramatic, but conceptually similar. Webb is showing us something unexpected about the early universe. Whether that leads to a minor adjustment in our models or a more significant shift remains to be seen, but the process is the same. Gather data, test ideas, refine our understanding. What's frustrating for many people, both scientists and the public, is the uncertainty. The desire for definitive answers is strong. Did we find galaxies older than the universe or not? Is Lambda CDM right or wrong? But science doesn't always provide yes or no answers on demand. Sometimes the answer is, we're not sure yet. We need more data. We need to rule out alternative explanations. We need to understand the systematics in our measurements. That's unsatisfying, but it's honest. And honesty, in science, matters more than certainty. Better to say, we don't know, than to claim we know something we don't. Better to acknowledge the limits of our understanding than to pretend those limits don't exist. The universe is under no obligation to be easily comprehensible. It's vast, ancient, complex. We're doing our best to make sense of it with the tools and minds we have. The James Webb Space Telescope is one of those tools. It's an extraordinary instrument, the result of decades of work by thousands of engineers, scientists, technicians. It sits at a gravitationally stable point, 1 million miles from Earth, its mirror unfurled, its instruments cooled to just a few degrees above absolute zero. It stares into the darkness, collecting photons that have traveled unimaginable distances. And those photons, when analyzed carefully, tell us stories about the universe's past. Some of those stories confirm what we expected. The universe is filled with galaxies. Those galaxies are made of stars. The stars formed from gas. The gas came from the Big Bang. Structure grew from tiny fluctuations amplified by gravity over billions of years. All of that fits the picture we've been building for a century, but some of the stories are unexpected. Galaxies that formed earlier than anticipated, structures that assembled faster, masses that exceed what the timeline seems to allow. These are the stories that challenge us, that push us to think harder, to question our assumptions, to consider possibilities we might have dismissed before. And maybe that's the real value of these observations. Not that they definitively prove Lambda CDM wrong or right, but that they force us to confront the fact that we might not have the whole picture. They remind us that the universe is bigger, stranger, more complex than any model we construct. They keep us humble. There's a tendency, especially in popular discussions of science, to present discoveries as either confirmations or refutations. Either the theory is right or it's wrong. Either we understand something or we don't. But the reality is messier. Theories are tools for understanding, and like any tool, they have limits. Lambda CDM is an excellent tool for describing the universe on large scales and over most of its history. But it might not be the right tool for every question. It might need refinement at the edges, in the extreme conditions of the very early universe, or in regimes we haven't explored carefully enough. That doesn't invalidate everything it tells us. It just means we need to be thoughtful about where it applies and where it doesn't. The process of refining our understanding is slow. It involves thousands of astronomers around the world, working on different pieces of the puzzle. Some are observing with Webb, pointing it at different patches of sky, different types of galaxies. Others are working with complementary telescopes, ground-based observatories that can study nearby galaxies in detail or survey large areas of sky to understand the overall population. Still, others are working on the theoretical side, running simulations, developing new models, testing different scenarios to see which ones match the observations. The simulations are particularly important. To understand how galaxies form, you need to simulate the evolution of matter in an expanding universe over billions of years. You start with the initial conditions, the tiny density fluctuations present in the early universe, and you let physics take over. Gravity pulls matter together. Gas falls into dark matter halos. It heats up, cools down, forms stars. Those stars produce radiation and winds that push gas around. Some stars explode as supernovae, injecting energy and heavy elements into their surroundings. Black holes grow and launch jets. Galaxies merge with each other, triggering bursts of star formation. All of these processes have to be included in the simulations, at least in some approximate way, and that's incredibly difficult. The range of scales involved is enormous. The entire simulation might cover a volume millions of light years across, but star formation happens on scales of light years or less. You can't simulate both at full resolution. You have to make approximations, use simplified models for small-scale processes, and hope those approximations capture the essential physics. When you run these simulations with the standard Lambda CDM parameters, you get a universe that looks a lot like the one we see. Galaxies form. They grow over time. They develop spiral arms and bulges and all the features we observe, but the details matter. If you compare the simulated galaxies to real galaxies in detail, there are discrepancies. Simulated galaxies often form too many stars too early, or they form stars too slowly later on. They might have too much gas or too little. Their structures might be slightly different. These discrepancies are usually addressed by adjusting what's called the subgrid physics, the simplified models for processes that happen below the resolution of the simulation. Star formation, supernova feedback, black hole growth, stellar winds. By tweaking how these processes are modeled, you can make the simulated galaxies match observations better. And that's fine. Those subgrid models are meant to be adjustable because we don't fully understand the detailed physics anyway. But with the Webb observations, the discrepancies are more fundamental. It's not just that the simulated galaxies don't quite match the observed ones. It's that the simulations aren't producing enough massive galaxies at early times, even when you adjust the subgrid physics. The overall timeline seems to be the problem. There just isn't enough time in the simulations for galaxies to grow as massive as the observations suggest. Some researchers have tried running simulations with different assumptions. What if star formation efficiency was higher in the early universe? What if supernova feedback was weaker, allowing more gas to remain in galaxies and form stars? What if dark matter clumped more efficiently? These variations can increase the number of massive early galaxies, but often at the cost of breaking something else. If star formation is too efficient early on, you end up with too few gas-rich galaxies later. If feedback is too weak, you don't match the observed properties of present-day galaxies. It's a balancing act. The model has to explain not just the early universe, but the entire history. Any change you make to address the early galaxy problem has to be consistent with everything else we know. And that's what makes this challenging. The observations aren't just isolated data points. They're part of a larger web of evidence, and everything has to fit together. There's also the question of what we mean by a galaxy in the early universe. Today, when we talk about a galaxy, we have a clear picture in mind, a gravitationally bound system of stars, gas, and dark matter, something like the Milky Way or Andromeda. But in the early universe, galaxies might have been very different. Smaller, less organized, more irregular. The massive galaxies Webb is seeing might not be single, coherent objects. They might be collections of smaller clumps that haven't fully merged yet. Or they might be in the process of assembling through continuous streams of inflowing gas. This matters because how you define a galaxy affects how you count them. If you're looking at a region of the early universe and you see several bright clumps close together, do you count that as one galaxy or several? The answer depends on whether those clumps are gravitationally bound to each other, whether they'll eventually merge into a single system. But from a distant observation, it's hard to tell. You're seeing a snapshot, a single moment in time. You can't watch the system evolve to see what happens next. Some of the mass estimates for early galaxies might be including material that isn't really part of the galaxy yet, gas that's flowing toward it, clumps that are nearby but not yet merged. If you're overestimating what constitutes a single galaxy, you will overestimate its mass. And that could partially explain why some of these galaxies seem so massive. They might actually be multiple smaller systems that appear as one in the observations. But again, this doesn't resolve everything. Even accounting for these effects, the overall population of massive structures at high redshift seems higher than expected. The discrepancy is reduced, but not eliminated. Another angle involves the role of supermassive black holes. Most large galaxies today have a supermassive black hole at their center, millions or even billions of times the mass of the Sun. These black holes grow by accreting matter, and as matter falls in, it releases enormous amounts of energy. That energy can heat the surrounding gas, drive powerful winds, and regulate star formation in the galaxy. Webb has found evidence of active black holes in some of the early galaxies. The galaxies show bright, compact cores with spectral features that indicate energetic processes. If these black holes were already massive at early times, they could have influenced how the galaxies formed. But that raises another question. How did the black holes themselves get so massive so quickly? Supermassive black holes are thought to grow from smaller seed black holes, which could form from the first generation of stars or from direct collapse of gas clouds. Those seeds would then accrete matter over time, growing larger. But accretion has a limit. There's a maximum rate at which a black hole can grow, determined by the balance between gravity pulling matter in and radiation pressure pushing it out. That limit is called the Eddington limit. If black holes grow at the Eddington limit, they can roughly double their mass every few tens of millions of years. Starting from a seed of a few hundred solar masses, you can grow to a million solar masses in a few 100 million years. That's fast, but is it fast enough to explain the black holes Webb is seeing? Some of the early galaxies seem to have black holes that are already millions of solar masses. If the universe is only a few 100 million years old, at the time we're observing them, those black holes must have grown very efficiently. Either they started from unusually massive seeds, or they grew faster than the Eddington limit, or both. Super Eddington accretion is possible under certain conditions, but it requires specific environments: dense gas, efficient cooling, maybe minimal feedback from the black hole's radiation. The connection between black hole growth and galaxy formation in the early universe is still being worked out. It's possible that the two processes are more tightly coupled than we realized. Maybe black holes don't just grow within galaxies. Maybe they help galaxies form in the first place by creating the conditions for rapid star formation. Or maybe they regulate galaxy growth by heating gas and preventing it from collapsing. The relationship is complex, and the observations from Webb are adding new constraints to how we think about it. There's also a philosophical dimension to all of this that's worth reflecting on. We build models of the universe based on observations we can make from one location, in space and one moment in time. We're standing on a small planet, orbiting an average star in an unremarkable galaxy, and from here, we're trying to understand the entire cosmos. We're looking at light that's traveled billions of years to reach us, and we're using that light to infer the properties of objects we'll never visit, events we'll never witness directly. The fact that we can do this at all is remarkable. The fact that our models work as well as they do is extraordinary, but it's also humbling to realize how much we're inferring. How many layers of interpretation separate the raw observations from the conclusions we draw? Every measurement depends on calibration. Every distance depends on a model. Every age depends on assumptions about cosmic history. When we encounter observations that don't fit our models, it's an opportunity to examine those assumptions, to ask which ones are solid and which ones might be provisional, to consider whether we've been too confident in aspects of our understanding that are actually more uncertain than we acknowledged. The early galaxy problem is, in some sense, a problem of confidence. Lambda CDM has been so successful that it's easy to treat it as definitive, as the final word on cosmic history. But science doesn't work that way. Every theory is provisional. Every model is an approximation. And the best models are the ones that not only explain existing observations, but also make predictions that can be tested. When those predictions fail, when observations surprise us, that's when science advances. The surprises from Webb aren't failures. They're data points. They're information the universe is giving us about how it actually behaves, as opposed to how we thought it behaved. And our job, as scientists, as curious humans, is to listen, to take that information seriously, to let it guide us toward a better understanding. This doesn't mean abandoning everything we've learned. The vast majority of what Lambda CDM tells us is still valid. The universe is expanding. It had a hot, dense beginning. Structure formed from gravitational instability. Dark matter and dark energy are real components. Even if we don't fully understand them, these pillars remain solid. But the details, the specifics of how galaxies formed in the first few 100 million years might need adjustment. And that's okay. That's how science works. You start with a broad framework, and you refine it as new data comes in. You don't throw out the framework unless it fails catastrophically. You adjust it, improve it, make it more accurate. The coming years will bring more observations from Webb, deeper surveys, more spectroscopy, better statistics on the population of early galaxies. Complementary observations from other telescopes will add context. Ground-based surveys will study nearby galaxies in unprecedented detail, helping us understand the processes that shape galaxies in environments we can observe more easily. Space-based X-ray telescopes will study the black holes in early galaxies. Radio telescopes will map the distribution of hydrogen gas. All of this data will feed into the models. Theorists will refine their simulations, test new ideas, explore parameter space more thoroughly. The field will converge on explanations that account for the observations without breaking what we already know. It might take a decade, it might take longer, but gradually the picture will come into focus. And maybe, at the end of that process, Lambda CDM will emerge mostly intact, with a few adjustments to how we model star formation or black hole growth in the early universe. Or maybe we'll discover that something more fundamental needs to change. Maybe dark matter behaves differently than we thought. Maybe the expansion history has features we missed. Maybe there's a new component or process we haven't considered. We don't know yet. And that uncertainty, that openness to different possibilities, is what keeps science honest. It's what prevents us from becoming too attached to our models, too convinced of our own understanding. The universe doesn't care what we believe. It just is. And our models are only as good as their ability to describe what is. There's a certain beauty in that, in the way the universe resists easy explanation, in the way it keeps surprising us, keeps revealing new complexities. If everything fit neatly into our models, if every observation confirmed our predictions, science would be less interesting. It would be bookkeeping rather than discovery. The fact that we're still being surprised, still encountering puzzles, means there's more to learn, and learning is what science is for. The galaxies Webb is seeing formed in a universe we're only beginning to understand. They assembled from gas that had just begun to cool after the Big Bang. They ignited the first generations of stars, enriched the cosmos with heavy elements, grew and merged and evolved into the structures we see today. They're not anomalies, they're not mistakes, they're real objects with real histories, and they're telling us something about the conditions in which they formed. Our models said they shouldn't be there, or shouldn't be as massive, or shouldn't have formed so quickly, but they are there. So either our models are incomplete, or our measurements need refinement, or both. Figuring out which is the work ahead. What's striking is how quickly this field is moving. Just a few years ago, the early universe was largely invisible to us. Hubble could see hints of distant galaxies, but they were faint, hard to study in detail. Webb has changed that. It's opened a new window, given us access to epochs we couldn't observe before. And with that access comes new questions, new puzzles, new opportunities for discovery. The next generation of telescopes is already being planned. Ground-based instruments with mirrors 30 or 40 meters across, space telescopes designed to study Earth-like planets or map the distribution of dark matter. Each new instrument will add to the picture, fill in gaps, test predictions. The work doesn't stop. The questions don't end. Every answer leads to new questions. And maybe that's as it should be. The universe is vast and ancient, and we're newcomers, trying to make sense of it with tools we've invented and minds that evolved to navigate a very different environment. The fact that we can understand anything about cosmic history is astonishing. The fact that we're still discovering, still learning, means we're not done yet. The light from those early galaxies traveled for over 13 billion years to reach us. It passed through expanding space, through regions where galaxies were forming and stars were being born and black holes were growing. It carried information about all of that, encoded in wavelengths and intensities and spectral lines, and now, captured by a telescope floating in space, analyzed by computers and careful human thought, that light is telling us its story. It's a story that doesn't quite match the one we expected, and that mismatch, that tension between observation and theory, is where we are now, standing at the edge of our understanding, looking at data that challenges what we thought we knew, trying to figure out what it means. The phrase, older than the universe, captures that tension. It's not literally true. The galaxies aren't older than the cosmos that contains them, but the way they appear in our observations, the properties we infer from their light, create a paradox within our models. They seem to require more time than was available, more efficiency than we expected, more mass than should have assembled so soon. That paradox is a gift. It's the universe telling us to look harder, think deeper, question our assumptions. It's an invitation to understand better, to refine our models, to keep exploring. And that's what makes this moment in cosmology so compelling. We're not at the end of understanding. We're in the middle of it. We're watching our picture of the universe shift and adjust as new information comes in. There will be more observations, more analysis, more debate, more refinements, and eventually, one way or another, we'll figure out how to reconcile what Webb is showing us with what we thought we knew. We'll understand how those early galaxies formed, why they're so massive, what it means for cosmic history. But even then, even when we've solved this particular puzzle, there will be others. New observations will raise new questions. The universe will surprise us again in ways we can't anticipate, and we'll do what we've always done. We'll observe, we'll measure, we'll think, we'll build models and test them and revise them. We'll keep learning, because that's what it means to study the cosmos, to stand beneath a sky full of stars and ask how they came to be, to look at light from the edge of everything and try to understand what it's telling us, to build instruments that can see farther and more clearly than our eyes ever could, to construct theories that connect the very small to the very large, the very early to the present moment. The James Webb Space Telescope is showing us galaxies from the dawn of time. Some of them fit our expectations, others don't, and in that mixture of confirmation and surprise, we find the path forward, not a path to certainty, but a path to deeper understanding, not an end to question, but better question, not the final picture, but a clearer one. The light keeps coming. Ancient photons from ancient stars in ancient galaxies, arriving at our instruments one by one, carrying their stories across the void. We gather them, measure them, think about what they mean, and slowly, carefully, we piece together the history of everything. Some of that history surprises us, some of it challenges what we thought we knew, and that's how it should be. The universe doesn't exist to confirm our theories. It exists, and we do our best to understand it. When our understanding falls short, we don't blame the universe. We look harder. We think differently. We remain open to the possibility that reality is stranger, more complex, more interesting than we imagined. That openness, that willingness to be surprised, to be wrong, to revise our understanding, is what science requires. And it's what the early galaxies are demanding of us now. They're demanding that we take them seriously, that we figure out how they came to be, that we adjust our models or our measurements or both until everything fits together. We don't know yet what that adjustment will look like. We don't know if it will be minor or major, a footnote or a revelation, but we'll find out because the data is there. The observations are real, and somewhere in the tension between what we see and what we expected, there's truth waiting to be uncovered. The galaxies aren't older than the universe, but they're teaching us that the universe might be more than we thought, more complex, more surprising, more worth understanding. And in the end, that's all we can ask for, a universe that keeps us curious, keeps us questioning, keeps us reaching for better answers. The light continues its journey, the telescope continues its watch, and we continue our work, trying to make sense of the cosmos, one photon at a time, at